Welcome friends. In the last session, we have discussed the 2 wattmeter method of the power measurement. So we have understood that different conditions for power measurement, and we have also understood that if the angle between voltage and current are changed, the wattmeter readings will change accordingly. Now in this session we shall demonstrate few problems through which the aspects of this topic or this the power measurement topic will be clear. So let us consider this problem. The problem statement is that we have a balanced Y connected load of 50 minus 36.9 degree ohms. So that means we have a load impedance of 50 angle 36.9 degree. That means this is power factor angle phi. So the angle between voltage and current is this 36.9, so which is equal to, so therefore power factor becomes 0.8. So that is the first information we can have from this first line of the problem. So we have a load power factor of 0.8, of course lagging, because the current is here, this angle is negative, so that is why it is a lagging. Now it is connected, this Y connected load is connected to the 400 volt 3-phase 50 Hz supply. So this side is supply, this is supply side, 3-phase 400 volt 50 Hz AC supply. Now the problem statement is that 1 wattmeter is connected in various manner as shown in figure 8. So we have 4 figures in figure 8. That means sub figure A, sub figure B, C and D. We have 4 sub figures where the wattmeter connection, different wattmeter connection is shown. That means if you consider figure A, you see current coil is connected to the R phase in series. However, the pressure coil of the wattmeter is connected across R and N. N means neutral. It is an example of a 3-phase 4-wire system. So this connection is done with respect to, or the pressure coil is connected. So this is C terminal and this is V terminal. So this pressure coil has been connected across R and N terminal. This is N terminal, neutral wire. Where from this neutral wire? This is the neutral point. Okay, this is the neutral point from where it is connected. So basically, pressure coil so for the sub figure shown A, wattmeter measures IR. Wattmeter measures IR through its current coil, and the pressure coil it measures only VR. Simple. It is VRN or VR, it is same. So VR is measured using its pressure coil and IR is measured using its current coil. Now if you consider the figure 2 or figure B rather, sub figure B, the connection diagram of the current coil is same. It is measuring IR current. However, for this time pressure coil is connected across R and Y terminal. You see, pressure coil is connected across R and Y terminal. In this way the connection is changed. So connection or current coil measures a current of IR that is fixed, that is not changed. However, the potential coil now this time measures the voltage of VRY. Now for the third case, figure C, again the current coil connection is same, which is measuring IR. However, this time for the pressure coil it is measured across R and B terminal or R and B phase. So this is R2C and this terminal is V. So this is V2, it is straight going to B terminal. So for the sub figure C, its current coil measures the current IR and its pressure coil or potential coil measures the voltage of IRB. And for the last diagram, again the current coil remains same. The connection diagram of the current coil remains same as it is. However, this time the potential coil is connected across Y and B terminal. Potential coil is connected across Y and B terminal. So we have understood 4 diagrams where we can see that for each case current coil connections are remain same. However, for each case potential coil is changed. For the first time, for the case number 1 or figure, figure it is 8A. For the figure 8A, it is actually voltage is VR and current is IR. For figure 8B, voltage is V, this 8B, this figure, the voltage is VRY and current is IR. 8C, figure 8C, voltage this time will be RB and current will be IR. And for the last diagram 8D, voltage this time now will be VYB and current will be same IR. So what is the power consumption for each case? Will it be equal or will it be difficult or will it be different? Let's see. So if you go back to the previous, or if you go back to this diagram, you see for the first case, the voltage is this. For the first case, the voltage measure was VR and the current was VIR and the angle between them is 36.9 because phi was 36.9. So if you consider this phasor diagram, so this is the connection diagram of the figure 8A. Okay, this is the connection diagram. So you see this is VR and this is IR and angle between them is 36.9 degrees. So the power consumption will be VR into IR cos 36.9. So what will be VR? VR is nothing but this value 230.9 volt. So this is 230.9 volt because it is representing phase voltage. IR represent phase current. So this is the IR 4.62 ampere. And cos 36.9 we have already mentioned power factor is 0.8. So if you solve this for the first case, if you connect your wattmeter in this way, it will give you a reading of 853.4 watt. It will give you a reading of 853.4 watt. Now the voltage, phase voltage becomes 230.9. So the current becomes phase voltage by its impedance, that will be 4.62. Impedance is this. Now if you consider the second diagram, The current is IR, it is okay, but now it is measuring the pressure coil through by its pressure coil. It is measuring VRY. Now, if you go back to the the diagram, phasor diagram, VRY is this. VRY is this phasor, and this angle is 30 degree, and this angle is 30 degree. So the angle between VRY and IR is basically 30 plus phi. It is basically 30 plus phi. So let us see. So we have seen this diagram or this phasor diagram. So this is VRY and this is IR, and the angle between them is 30 plus 36.9, so it will be 36.9. So this angle is 30 and this angle is 36.9. So altogether it will be 30 plus 36.9 will be 66.9. So now if you solve this, now VRY, now it will measuring VRY. So VRY is 400 volt. VRY is 400 volt. IR is 4.62. We have evaluated 4.62. However, this angle becomes now 66.9 instead of 36.9. So we evaluated this term as 0.39. So if you solve, now this time power becomes 720.72 watts. So power reading reduces. So if you changes from figure A to figure B or connection A to connection B, your power reading reduces from 853 watt to 720 watt. That is a very strange thing. Same wattmeter, same circuit, but power rating or reading of that wattmeter is changing. It is mainly due to your connection of the potential coil. Each time you are changing your connection, this angle will change. This phase angle, that phi will remain, phi will keep changing. That is why this reading will also changing. Now if you go to the next diagram or next case, case C. So now this time the current coil is same IR, but this time voltage is now VRB. Voltage is now VRB, which is equal to 400 volt. VRB is equal to 400 volt. IR is equal to 4.62. We have measured previously. Now what about the angle? So let us check VRB and IR. So where is VRB? VRB is this. VRB is this. So you can understand this angle was 30 degree. This angle was 30 degree. And this was 36.9 degree. So angle between IR and VRB, that is 36.9 minus 30. So it is only 6.9 degree. But this time the diagram is little bit different. That means if this is VR, if this is VRB, it is 30. So this should be the direction of IR. It is even lagging by a VRB by another 6.9 degree. So this is 36.9 degree, right? So the angle between, the VRB and IR is becoming 6.9 degree. This actually 6.9 degree. So exactly what we have understood here. So this is VR and this is IR, and this angle is 36.9. So this angle must be 6.9 degree. So if you solve this, it will be 1829.5. So you see how big the reading is, how large the reading is. It is more than 2 times. More than 2 times. Okay. So again, it is again one more time the reading is changed due to the different connection of wattmeter. And when you finally reached at our last diagram, now this time this pressure coil is connected across Y and B. So this time this pressure coil is measuring VYB. So if you go back to the previous diagram, so what is VYB? VYB is this pressure VYB, right? So the angle between VYB and IR, so this is actually 90 degree. This angle is 90 degree, and you know this is actually 36.9. So the angle between them is 90 minus 36.9. 90 minus 36.9, which is equal to 53.1 degree. So let me again coming to this figure. So this is VYB. So this is 90 degree. So this is 36.9. So the angle between IR and VYB is equal to 53.1 degree. So this is 53.1 degree. Again, VYB is equal to 400 volt, IR is equal to 4.62, and cos 53.1, it is not 0.99. This is wrong. I think 53.1 is 0.6. So if you solve this, it will come as 1108.8 watt. 1108.8 watt. You can also verify. So what we have understood that for the first case, the reading was 853.4 watt. For the second case, the reading was 720.72 watt. For the third case, the reading was highest 1829.5 watt. And the fourth case, the reading was 1108.8 watt. So totally depends on the wattmeter connection. The same wattmeter. Interesting thing is that the same wattmeter, same load, same voltage, same current. However, just the connections of potential coils are changed. So due to that fact, the readings of the individual connections are changed. That is a very important observation. Now we have another problem. It is said that a 3-phase 400 volt 415 volt load has a power factor of cos phi. 2 wattmeters are connected to measure the power, which shows the input to be 10 kilowatt. So we have the total power of 10 kilowatt, that means 10,000 watt. That is P1 plus P2. So what is P1 plus P2? We have know one formula. We know one formula, root 3 VL IL cos phi. That is equal to total power, which is 10,000. So that is why root 3. What is VL? Line voltage is 415 volt. Current is unknown. And cos phi is, 0.7, it is mentioned. It is 10,000. So if you solve this, you will get IL, that is the line current, is equal to 19.9 amperes. Now you need to evaluate, find the readings of each wattmeter. What is the P1 and what is P2? So P1 minus P2, similarly we have formula root 3 into V phase I phase sin phi. This is the equation. Yes. This is the equation root 3 V phase I phase sine phi, that is P1 minus P2, equation 16. So that we have utilized here. So P1 minus P2 is equal to root 3. So root 3 into V phase, that is VL into IL into sine phi. So if you substitute, VL is equal to 415 volt, IL is equal to 19.9, and sine phi is equal to 1 minus 0.7 whole square under root. So if you solve this, you will get this result, 5863.5 watt. So this is your equation number 1. P1 plus P2 is equal to 10,000 watt. If this is your equation 2, P1 minus P2 is equal to 5863.5 watt. So if you solve these two, you will get a solution of P1 is equal to 7931.75 watt and P2 is equal to 2068.25 watt. So in this way, we have solved two problems. We have seen solving two problems for star networks. From the next class, we will start discussing delta network or delta load or pi load. In this lecture, we have primarily seen that a demonstration, a numerical example, how wattmeter readings are changed depending on its connection. So with this, I am ending here. From the next class, we shall discuss more on this. Thank you.